Good morning, everyone. This is Aravind Seshadri from Roll2Roll Technologies. I'm here today to talk about advanced web guiding applications and concepts. Before we begin, let's look at some of the basic concepts regarding edge guiding, center guiding, sensor positioners, moving sensor center guide. What do we mean by guide point? What do we mean by remote guide point? What is a deadband? And what is edge filtering? We will use these concepts to build on so that we can look at how some of the challenging guiding applications can be solved by some of these things that we initially cover. So everybody is familiar with edge guiding. If not, edge guiding or guiding basically is to align the cross-machine direction position of the web within a roll-to-roll machine. So you're laterally positioning the web at a certain location in the cross-machine direction of the web. This is typically done with a single sensor, and the sensor measures the position of the web and sends that information to a control system. And based on the measurement and the reference, there's an error that is computed, and then the control system sends the command to the actuator, and then the mechanism, the web guide mechanism, moves the web, and then this is a closed loop control system that keeps going on. Typically, one sensor or two sensors are used, and in a single edge guiding application, the sensor may be installed on the drive side or on the operator side, depending upon what is required. And then the sensor is typically positioned at a constant or a predefined reference within the machine so that the web can be guided to a certain position within the machine. Now, the main issue with a single sensor web guiding application is that whenever the web width changes, then somebody has to go move the sensor, and depending upon your process, if the process is aligned to the center of the machine, or if it's justified to one side of the machine, the sensor might have to be moved at different locations. And anytime when you have to move a sensor, that causes downtime, and it also introduces an opportunity for error and operator error. So that's the main issue with edge guiding with a single sensor. Apart from edge guiding, there are some situations in which center guiding is used, where you have two sensors, each of them looking at one edge of the web, and then they send the signal to the controller, and the controller averages those two measurements, and then based on that average measurements, it computes the error, and then it moves the actuator based on the error. The main reason why the center guiding is used is in applications where there is an inherent possibility of a slight variation in the web width. Let's say you have an extrusion process, you're extruding the web, but it's not a straight edge. It might have some amount of variation there. To reduce the effect of either justifying to one side, where you might have a perfectly round roll on one side and then a really jagged edge on the other side, it's common for manufacturers to use two sensors to center guide the web. Now, even with the center guiding application, when the web width changes, somebody has to move the sensors. And again, like a single sensor, you need to move it at the right location. And now you have two sensors that needs to be moved. And then these two sensors have to be positioned exactly equidistant from the center line. All of these causes time. And if there is an error, then it causes downtime as well. So in order to avoid this, some manufacturers have what is called as automated sensor positioners. Instead of manually moving the sensor, you can automate that by connecting an actuator to the sensor, and you can move one or two sensors based on what product you are running, and you can automate it by setting all of those into the PLC so that based on the product code, the sensor is moved automatically. This does reduce the downtime, and then it also helps reduce the operator error. But this system is a little bit complicated because you have a system, like an actuator, it needs another control loop to move the sensors. And if those sensors have to move automatically without an operator kind of pressing a button to get it to the different location, then you have an additional control loop in there. That increases the complexity of the system. And then when you have an additional control loop, you also need to tune the control loop. So if the web width kind of varies like this, and if the sensor is automatically moving, it's oscillating back and forth, then the gains of those system has to be adjusted just right so that it doesn't never miss the web, and then it's not too aggressive that it can run into the web and damage the web. So this increases complexity, additional actuators, additional drives that are involved, and overall it adds more mechanical wear and tear to the system. A better way of doing this is to just have a wide sensor. If your sensor is wide enough to accommodate any web width variation, then there's never ever a need to move the sensors. And you can put one sensor on each edge. So you have a center guiding application with two sensors. And if the web width varies, and if the sensor is wide enough to see all of the variation, then you would never have to move the sensor, and you can still do that. One of the key things in accomplishing this is basically what we call as a guide point. So when you have a single sensor and you're guiding the web based on the measurement from the sensor, the control system is going to use a reference signal. And that reference is usually the middle of the sensor's position measurement. So if the sensor has an output of 0 to 10 millimeters, and 5 millimeter, for example, would be the reference. And if the web goes at 4 millimeters, or if the web is at 6 millimeters, then there's an error that is being created. Based on the magnitude and the direction of the error, the control system sends the command to the actuator to move the web guide. And most often, the guide point or the reference is in the middle. In this case, it's 5, like what I mentioned. Now, instead of moving the sensors manually, what can be done is actually move the reference within the sensor. So instead of guiding to 5 millimeter, when the web width changes, you can guide to 2 millimeter as the reference. So if the web is at 1 millimeter, it creates a negative error, and then when the web is at 3 millimeters, it creates a positive error, and now your guide point is moved to 2 millimeters. And this is what is called as an electronic guide point change. The main advantage with electronic guide point change is that if you have a sensor that is pretty wide, and let's say you have a sensor that is 17 inches wide, then any web width variation, you don't have to move the sensor so that the web can be guided to the middle of the sensor. You can just electronically move the guide point to a location so that the web can be guided at that location. And this is a simple thing that can be done. It can be automated easily, and then you don't have any mechanical wear and tear because everything is fixed and you never have to move the sensor. And this is what is illustrated in this animation here, where if the guide point is to the left or to the right, then the reference for that control system is going to be at that location, and then the actuator is going to change direction at that arbitrary location. So you can technically have the guide point anywhere within the sensing window, but it is very common to limit the extremes so that you don't put your guide point all the way to one edge or all the way to the other edge. The main reason is that once the web moves past that edge, irrespective of where it is, it's hard for you to know what's happening there. So you want a little leeway so that you don't go all the way to the extreme on either direction. So it could be like you can go up to 90% of the sensor range. That's where the guide point can be changed. But within that remaining 5% on either side, you cannot change the guide point. So this is what is called as an electronic guide point change, and it's very common, especially with a wider sensor. And this enables operators to not to move the sensor and have a quick product changeover. And then when we do center guiding, the guide point change actually you don't need to do a guide point change when you do center guiding, especially with two sensors. And that's what this math is showing, is that even if you move the sensors on either direction, the guide point doesn't change. So this is making it a lot more simpler. So center guiding with two sensors is a lot more simpler than edge guiding. And then even when the web weight changes, you never have to change the guide point. So these are the advantages. Like I mentioned, center guiding with a wide sensor is a lot more simpler, reduces the mechanical wear and tear. Inherently, it averages, so that's like a filtering. And then it's simple to install, operate, and then helps you with the quick product changeover. And then you can use this sensor as a web detect sensor, and as well as to monitor the width of the web, because you can see both edges of the web. Another concept that is commonly used is what is called as a deadband. A guide point is the reference from which the error sign changes. Now, deadband is a region around the guide point where we can still say the error is 0, and then beyond the deadband is when the error becomes positive or negative. And this is done mainly to avoid any issues with artificial edge position variations that are created by edges that are kind of fuzzy or rough, where the web is actually not moving, just that the edge is kind of jagged. In order to avoid the web guide from moving back and forth, we can use a deadband onto it. And finally, a concept called edge filtering. It's basically, instead of taking the measurement, instantaneous measurement, you can filter the data in time. And a typical filter that is commonly used is an exponential moving average filter. And this helps in significantly reducing the variation of the edge position, especially when you have some kind of an edge that is jagged and it's not really representative of the actual web position, but just that the edge is kind of jagged like that. This plot is just showing how if you have a standard deviation of 7, and then if you do a filtering, for example, you can reduce that variation by 50%. And then if you do an averaging with that, you can reduce that even further. So the top plot is showing the measurement from one sensor, the bottom plot is from another sensor, and then the middle plot is the average of those two sensors. That would be the center line, center guiding kind of thing. So looking at some examples. Let's say you have an edge like this. The web is pretty jagged, and this is from an extrusion process. Now, you don't want to take the instantaneous measurement and guide the web, because the web guide is going to be oscillating back and forth. It's going to be crazy. What better way to do this is to use two sensors, so you get an inherent averaging of those two edges, and then add a deadband. Basically, if you have an idea of the profile of this edge that is varying, based on that, you can create a deadband value and then filter the edge position, so that the steady state or the gross position of the web would be at a fixed location. And then even when the edge measurement is not that great, you can still have the web guide to not oscillate. Instead of, there are situations where you deliberately have an edge with a certain profile, like what is shown here, and it's got a sawtooth kind of profile. The main problem with this is that none of the conventional techniques would work, because that when this web goes underneath the sensor and you're looking at that edge position, depending upon the speed, depending upon the sensor measurement frequency, and depending upon the duty cycle of the sawtooth wave, when you do any kind of an averaging, you're going to shift the guide point. You're going to have that average move whenever any of those conditions change. For example, let's say you're running at 1,000 feet per minute and you do all of these things, and then now you go to 2,000 feet per minute. That's going to cause a shift, even if you do any kind of an averaging. So temporal averaging or time-based averaging is not a solution for that, but a spatial averaging or spatial filtering is a solution. In this case, you would align the sensor vertically along the machine direction and then have some kind of like a bang control to be able to guide the web. This is a technique that we use to guide some of these webs like this. Another common problem that we would see is wrinkles. Basically, what wrinkle is that whenever there's this trough and the valley that is created on the web, it's going to suck the edges in and out, in and out, in and out based on how the wrinkles are flowing. And this is going to cause an edge position variation, which is not representative of the web position. The edge may go in and out, but the web may be still in the gross position. So this affects a lot of systems, and the best way to tackle this is to do center guiding. And if you have any information about the wrinkles, you can have that, use that in your infinite impulse response exponentially moving average filter to reduce that effect, and then also use a deadband. So depending upon how much the width variation is, you can put that into your system. So let's say the wrinkle is causing the width to change by 1 millimeter, then you can add 0.5 millimeter of deadband on either side, and that would make sure that the wrinkle is not causing the web to oscillate. But in reality, these are all kind of like fixes, and these are not real solutions for the wrinkle problem. And in this case, you have to go in and fix the underlying wrinkle problem. To avoid the web guiding from oscillating, these are some things that we could do. And finally, there are situations where, especially in diaper manufacturing or nonwovens, where you're running a porous web, and then the sensor that you're using to run the porous web is affected by the porosity of the web. And what it essentially would do is, depending upon the density of the web underneath at that instant, when the sensor is making the measurement, that's going to change your output of the sensor. So the output of the sensor may be varying based on the density of the web at the instant that you're measuring. This will cause an artificial variation in the edge position, which is unwanted. And the best way to avoid this is to use a sensor that is more accurate, that is not affected by porosity variations and density variations. And if you cannot do that, then the other best way to do it would be to do some deadband and filtering, and depending upon how much accuracy you can achieve. So whenever you add a deadband and filter, you are reducing, by adding deadband, you're reducing the accuracy that you can get. And then by adding filtering, you are reducing the dynamic response, or how fast your system can correct that error. You're reducing those. So it's a trade-off based on what is the ultimate objective. And this is just an illustration kind of showing, like, when you have an artificial edge position variation, and then when you do a center guiding, you can see that the middle plot is the top plot is one sensor, the bottom plot is another sensor. And then when you do a center guiding where you take the average of those two, just by doing that, you're reducing the variation. And then if you add a exponential moving average filter to it, you're reducing it further. And then if you add a deadband to it, then you're reducing that even further. So this is shown in this table here, and you can see we start off with about 1 millimeter of standard deviation, and then by filtering, we got about 40% improvement. And then if you do filtering, exponential moving average, and deadband, you get about 70% reduction in the variations. And again, these variations are artificial. So the deadband and the exponential moving average, the filter time constants, have to be designed based on that information, that, hey, how much is the variation and things like that. All of these can be avoided if you use a sensor that is not affected by any of those. Finally, whenever we are looking at guiding a web, there may be situations where you might want to guide multiple webs. And this is true in lamination or coating or extrusion lamination, any of those scenarios. In those cases, you can typically guide 2 layers of the web independent of each other, and then guide it to the same machine reference. Then you can achieve proper lamination at this point. But the main problem with that is when the web width changes, or if there's any center line guiding kind of application, then you need a little bit more coordination between these two layers of the web. One of the things that has been done mechanically is to chase the web. And in that case, you have a master web that is there, and then there's a sensor that is installed to chase the web. It means that if the web moves 1 inch on one side, the sensor would actually follow and chase the web. So there's a control system that is kind of chasing the web. And that particular sensor is connected to the other sensor on the other layer. And this basically means like, okay, if the web moves on the bottom 1 inch, I'm going to move my sensor 1 inch on the top, and this is done automatically. So there is a control loop that is moving the sensor positioner mechanically. Obviously, you can see that it's a complex system. There's too many mechanical parts, and then depending upon how far these are, then the mechanical coupling is going to be an issue. And then if you want to do center guiding with this kind of system, then it just the complexity goes pretty high, pretty quick. A better way to do it would be to use the guide point or the electronic guide point adjustment. So you do have a sensor in the bottom, the master sensor, that is going to look at the position of the master web, and then it's going to provide a guide point adjustment to the sensor on the top, so that whenever the master web moves, the top guide point of the top web sensor also moves, and that makes sure that these two webs are coordinated. If you have multiple webs, multiple layers, then we do the same thing as what we did in the previous example. The only other thing is that there are two different web guide sensors whose position needs to be varied. So this is accomplished by slaving one of those. So this is a slave actuator. And this is the master actuator that is connected to this chasing sensor that is looking at the master web. This you would see commonly in metal industries, in lamination processes. Again, it's pretty complicated, especially mechanically. And then the synchronization, it's a common problem. Synchronization meaning that one actuator has to be exactly synchronized with the other actuator. Otherwise, this causes issues with performance, and then any lag or a slow response in one is going to provide an overall worse response for your system. The better way to do it would be to use an electronic guide point adjustment. Just use one sensor that's going to monitor this master web, and then change the guide point of the other slave webs or the follower webs, so that you can guide the web to that location. Now, the main considerations with coordination is that if you have this master sensor wide enough, then you can have the sensor basically look at any variation of the master web. And the master, in the examples that we showed there, the master sensor was just used for measurement, but technically you can also have a web guide on it, and that web guide is going to guide the web on the master web. And then that measurement can also be used to change the guide points on the slave or the follower webs. That can be done as well. And usually this has a good result if we can have the web path links with these different sensors and web guides from that sensor to where the lamination process is. If the web path links are the same, and that provides the best results, especially with dynamics and things like that. But if you can't, then you can use some kind of a feed-forward term to compensate for the additional spans that you have to work with. And then you can also do deadband or a feed-forward offset in these kind of things if you have to really put the sensor farther away from where you need to guide it. So that's a quick overview of some of the things about common things irrespective of what kind of a control system that you have, some advanced web guiding concepts. Now, we'll talk about some of the common control systems that are there in web guiding systems. We're just going to quickly go through some of these things. Most often, this is not addressed quite a bit, but we're going to take a quick jab at it. And then there are basically three main kinds, and then most of the web guides that are available in the market are fixed gain control systems, and they are feedback control. And then proactive control is a new concept, which is kind of like the future of web guiding. So in a fixed gain web guiding control system, as the name suggests, the gain is fixed. And like I said, a lot of people don't really know what's inside a web guiding system. There are multiple loops. There's a current loop, there's a velocity loop, there may or may not be a position loop, and obviously there's the outer edge position loop. All of these loops have gains, and these gains have to be tuned. And the main problem is that this web dynamics term right here, and that depends upon how fast you're running, what is the tension, what kind of elasticity of the web that you have, how is the web guide installed, all of those influence that. And then anytime you have a product changeover that can significantly change any of these dynamics, then the controller has to be tuned. Otherwise, it's not going to provide a good performance. Most often, most web guides, the controllers are not well tuned. That's a problem. Now, to overcome some of these, there are some other techniques called as adaptive control. The main idea behind that is instead of having a fixed gain control system, you have a controller that adapts, and it learns based on the current conditions, and it can avoid any sensor gain issues like the porosity issue that we talked about before. It can overcome those. It can adapt to the mechanical dynamics like the motor response and things like that, and also the mechanical advantage of the web guiding system. All of those things can be adapted to. And this is a little bit more advanced control system, and this is something that is also available. Another way of doing this is called optimal control. In this case, what it's done is if you know different conditions in which your web guide is going to be operated under, with all the different materials that you're going to run, all the different transport conditions, and all different installations if you have to, then an optimal controller, a fixed gain controller, can be designed so that it works best under all of these different conditions. And the optimal not just means in the control system, but also in the transport conditions, the installation, and things like that. So this is also available. I don't have a reference there in the bottom, but you can look at optimal web guiding on Google search, and you would find papers about this there. And finally, there are other control systems, especially those used in roll-to-roll products, is what we call as a nonlinear trajectory control. In this case, we control trajectories for position loop, velocity trajectories, and also have a predictive component to it. And essentially, it provides you with a pretty good response system, which is well damped. And in this case, we could achieve up to about 135 to 145 millimeters per second correction, which is kind of unheard of in the industry. And finally, this is kind of the future of web guiding, and this is what we call as proactive control. Instead of reacting to the edge position variations, can we be proactive about it? And this is something that we do. And one of the things here, the key thing here is that we have to first construct a performance index and then see whenever the performance index changes, what are the deterrents, or what are the things that are affecting that performance index? Is there a pattern to it? And from that pattern, can we see what is the root cause? Let's say there is a roller or web guide that is misaligned upstream. Can we detect that? And then can we provide that information to the operator so that they can go in and fix that problem rather than trying to react to it? An offset in an upstream process will actually limit the actuator stroke on the web guide in the downstream process, and this is unnecessary if you can detect it. And that's the whole idea behind a proactive control. It could be offset there, or a sinusoidal disturbance, or any of those kind of things where it could be material, process, or machine. And a proactive control system would be able to identify and provide some solutions for it. So in summary, some of the advanced web guiding concepts that we saw, that the simplest thing that anybody can do to get a good guiding performance is to do center guiding. and center guiding with wide sensors would significantly simplify your operation. If you need to do deadband or if you need to do edge filtering, especially you have some harder materials, you can do that. But essentially have a sensor that is unaffected by material property variations. That will help you. Coordination can be achieved with electronic guide point adjustment, and then the future is in proactive control. Do not react to the problems, be proactive and kind of figure out what is the underlying cause for it and how that can be fixed in your machine. That's my presentation. Thank you for your time. There are some additional resources here and also my contact information and how you can reach me. Unfortunately, I would not be available for the Q&A session, but I've asked one of my colleagues to be there. So hopefully if you have any questions, you would be able to address. Thank you so much for your time. Have a great day.